Hello, everyone. Can everyone online hear me? I heard some. Yeah.
它也叫 Joyce。
Okay. Okay, so you guys may see that the slides on lecture 3, we have the second half, which is the kind of laboratory or tutorial session. So that one, I guess in the latter slides, we also have some other parts about the tutorial sessions, and I will invite the TA to give you guys probably one night lecture with 3 hours about those tutorials. So I will not talk about it right now. Okay. So we will directly go to the lecture 4. Basically, I feel like we have probably 70 people already because you guys sitting here do not use Zoom, right?
Yes.
You're using Zoom?
No.
Oh, okay. That's good. So then I will feel like we probably already have 70 people, and it's good to start here. All right, today we are going to continue review the data analytics and data mining algorithms. Yeah, so in previous class, we have talked about the majorly the unsupervised learning algorithms. Majorly, they are the clustering families. We talk about k-means, we talk about hierarchical clustering. We also talk about DB-scan, right? So those unsupervised learning algorithms in systems development or systems modeling, they have basically been applied to address two issues. One is the dimension reduction. It's like, let me draw. So given a data set like this, so we have two-dimensional data sets, which is I use the traditional relational database to illustrate. So we have columns as attributes, okay, and rows as data points, okay. So the clustering algorithm using unsupervised learning strategy can typically apply into either, if we call number of data points as n and number of attributes as p, we denote those two as n and p, then we will say the unsupervised learning algorithm can be applied into address the dimension reduction in p as well as the sample reduction in n, okay. So when we talk about dimension reduction, the dimension typically refers to the number of features, okay? And number of data points, we usually say the sample size. So we will not say the dimension refer to the number of data points and the sample size refer to the number of attributes. We will not do that. Okay, so when we talk about the dimension reduction, is always reducing the value of p, the number of attributes, and reducing the sample size, okay, which is reducing the value of n So how can we do that? We use clustering to cluster similar attributes, okay, together probably as one, and we can use the centroids, the center value of these. For example, we group these three as one, and we're taking actually probably the average of these three as the center points, and to represent all of the three attributes by one, right? The same philosophy applies into number of n. For example, given if we have a data set has probably 1 million data points, we probably can use clustering to reduce it to 10,000. We can either use k-means, okay, by setting k equal to 10,000, or the other strategies, okay. The good thing is we can control the value of k to do the clustering, but definitely, if you want to do dimension reduction and sample size reduction by clustering, you need to evaluate the effectiveness of the cluster's performance, as I have mentioned in the previous class. You need to make sure that the clustering performance is effective when you do the dimension reduction and the reducing the sample size. All right, so today we are going to continue talk about the system modeling from the data-driven perspective. We have given the basic description of the data-driven system modeling, and today we are going to continue talk about it, and we will cover some of the classification tasks by introducing the classification algorithms, as well as later we will introduce some of the regression tasks and by introducing some data-driven regression algorithms. Let's recap some of the concepts. Today we are going to talk about developing some data-driven models for doing classification. So first we need to know what is the exact or very strict definition of the classification task. So first we need to have a data set to building up the model for doing classification. That means given a collection of records. So records can be referred to data points, and those collection of data points mean the training set. So if we have given a collection of records, we have a training data set, then each record can be characterized by a tuple, which is composed of x and y. This x is bold. You will see that it is a vector actually. So the vector means the attribute set, a set of attributes, okay? And y is the class label. So y itself can be binary or even have more values, can be categorical. And y can also be bold if the classification task consider multiple targets. That means multi-classification problem, okay? So given such kind of tuple representation, we will see that the X with bold typically describe a set of attributes, a set of predictors, a set of independent variables, or a set of inputs. So they are interchangeable. They mean the same thing, okay? Why they have so many names? Because nowadays data science comes from actually multiple domains. So some of the concepts in data science, they came from statistical learning, or more precisely applied statistics. And some of them comes from computer science, some of them comes from applied math, and some of them comes from engineering. So for example, in computer science, we typically call attributes, okay? And for statistics, statisticians, they probably prefer like predictors and independent variables. And in engineering, we typically describe like inputs, okay? So the Y denote the class, response, dependent variable, and output. So they're paired, attributes and class, or predictors and response. independent variable and dependent variable and inputs and outputs. Okay. And so given such kind of training data set characterized by a tuple X and Y, so the task of classification is we need to using those data points to learn a model which maps each attribute set X into one of the predefined class label Y. So once we have such kind of model learned, and in the implementation in the future, we aim to use the value of the attribute set X to decide the class or the label of the class Y, okay, the class label of Y. So this is a graphical illustration of the general procedure for building up a classification model. Usually we will have two sets of data. One is for training and another is for testing. So in each data set, we have first column is usually the index of the data points or data ID. Okay, here we refer to some transaction data, so it's TID transaction ID. Then comes with some of the X. Okay, so attribute 1, attribute 2, attribute 3, they can refer to little x1, x2, x3. So if some of you are not familiar with math, we will say this attribute 1 to 3 can refer to x1 to 3, and the bold X. So I will use this to describe the bold X is actually x1, x2, and x3. Okay, then the class is the Y. Okay, then we have Y. And basically we have such kind of tuple. So you can see here, the Y actually denotes the label of the class. It is, here is a binary example. And in the future, once you have the model, you basically have the input of the X, but you need to determine the value of the Y, okay? So the model development or training process, so we can tell people that in machine learning or in data-driven modeling, the model development or training models, they mean the same thing, okay? It's an induction process. Basically, it's a machine that conclude the rules or scientific findings from the data, okay? Then to describe approximate mathematical form for those underlying science and models. And we need to apply the learning algorithms and using an induction mechanism to build up the model, to learn the model. And you have a number of models developed, okay? Then you apply those models into a new data, then do the reduction, deduction, okay? All right. So that's generally the a general description of the classification task. Then next, we will describe the classification techniques. So nowadays, we actually have quite many types of classifiers, but we would like to talk about some basic ones like base classifiers, okay? They are actually classical, developed by the classical machine learning algorithms like decision tree based methods, nearest neighbors, neural networks, naive Bayes, support vector machines. It could be more. So why I say base classifiers, and because those classifiers, they were served individually. I mean, just one algorithm build up a classifier, okay? But there are also techniques which will integrate multiple classifiers together to process the classification task. And such kind of integration of multiple classifiers and their mechanisms is called ensemble strategy or ensemble techniques. And different ensemble techniques, including the boosting, bagging, and also the random forest also has a kind of ensemble structure, okay? So in this class, we will first start with some of the algorithms for developing base classifiers. We will probably first go with the very classical, very famous and most widely utilized classifiers, which is called decision tree. Okay. So this is a slide showing an example of a decision tree. So we again using the some of the data here, the training data as an example, but it's no longer transaction. So we have 10 data points with data ID 1 to 10. Okay. So the input will be the first three, and the last one will be the output. Okay. So here, different from the previous data sets, the three inputs, they are actually categorical. Okay, first two are categorical and the next one is continuous. And the class is binary. Okay. So based on these data sets, we're able to building up kind of decision tree, which has a tree structure, but it tells some logic or rules to help us to making decisions. So that's why we say it's decision tree. It's a tree structure of the model, which presenting rules to help us to make decisions. So how does decision tree look like? Basically, it will pick up one of the inputs as a node to do a kind of splitting, or in an applied perspective, is say we're picking a node or picking a parameter to generating a set of rules. Okay. And based on the results, we select another node to further generating rules to split. Okay. And so kind of. And then we will have the final outcomes. Okay. So if you want to see it's a tree, it's like this. So the top is always called root. Okay. And the bottom is always called leaves. If you cannot adapt it, you can rotate your head, okay? By probably, if you have the talent, you can rotate like 180 degrees, okay? Then you will see it is a tree. Okay, so so once you have the training data build up such kind of tree, then we apply the tree model into a testing data, and how can you generate the outcome? All right. So if we have such kind of test data, which offer the value of three-dimensional inputs, the homeowner, the marital status, annual income, then how can we classify the property of the defaulted borrower? Okay. So we start from the root of the tree. We first check the value of the homeowner. So it is no. Okay. Then we have to go to the second decision stage. We check the marital status. Okay. We see it is married. Okay. Then we can make a decision. It's the tag of the Y is no. All right. So if we're using the previous modeling procedure, the only difference here is the algorithm, okay, is actually tree model training algorithm, okay, or we call it tree induction algorithm. The algorithm for developing the model is a tree training algorithm, okay. So there could be a number of algorithms for training a tree or for developing a tree to make decisions. So famous ones including the classification and regression tree we call CART, and ID3, and as well as C4.5. So the C4.5 is the most famous, the most powerful, and widely utilized one. So we know that if we want to apply the decision tree algorithms to build up the tree model for making decisions, we need to have the data as the materials to feed the algorithm to develop model. Then in this tree decision tree induction process, what will be the design issues? Okay. So how should training records be split? Then we will talk about the methods for specifying the task conditions depending on attribute types. So you will see that when you do the induction of the decision tree, every time you're picking out a parameter as a node to split, you are actually basically setting up a hypothesis test. So if we go to very mathematical way, but usually we will not talk about it, just I'll go with the algorithm, okay? So the algorithm actually comes from such kind of, so when you're developing a tree, you have how many nodes, then you are actually making how many hypotheses. And the measure for, we also need to know the measure for evaluating the goodness of a task condition. That means you need to decide if we pick such kind of parameter as node for splitting, okay, to building up the tree, where such kind of strategy offer a good, actually offer a kind of goodness. Is that goodness good enough? Okay, every time we select the best parameter as the node to make the split. And how should a splitting procedure stop? That means we continuously selecting parameters as the node to split to grow the tree. Then when will be the time to stop our induction or training process? So we will usually stop splitting if all the records belong to the same class or have identical attribute values. That means we go to the very final decision node. So every records will find a home to stay with. Or we can set up the number of iterations to control our computational hurdle, okay? And also we can, based on such kind of number of attribute, number of iterations to do an early termination, okay? Then we need to talk about the methods for expressing the task conditions in developing a decision tree. So such kind of task condition can depend on the attribute types. Okay, so we need to concern the attribute types. We will have different strategies to address if the attributes is binary, if the attributes is nominal, if the attributes is ordinal, and if the attributes is continuous. And also, we also have the concern of the number of ways to split. So usually we will consider a very simple way, two-way split, but sometimes some of the methods or some of people will also consider multi-way split. That could make things very complicated. So the multi-way splits, first of all, let's talk about, illustrate the split strategy and its test conditions for nominal attributes. If we consider the previous data sets here, okay, so we check the Pareto strategy status, we will find that it has 3 values. And naturally, we will pick like a multiple way split. We want to split it to 3 with 3 directions. Okay, kind of use as many partitions as distinct values. That means that indicates one underlying knowledge or rules that you like to choose when you decide to split the node. You want to determine how many splits you should adopt, then you can check the values of that attributes. So in here, in our database, we'll find out the marital status, or based on our intuition and common knowledge, the marital status could just be 3, right? Single, divorced, or married. Then we can first do a multi-way splits, use as many partitions as distinct values. That means in this parameter, it has 3 distinct values. Then we split it to do a 3-way split one time. We can also choose the binary split. We can divide values into 2 subsets. So you have 3 values here. We can divide it to a number of combination of 2 sets. We can decide one set is married, another set contains both of single and divorce records, or we can set one set as single, another set as a combination of married and divorced, and last one is kind of one set is a combination of single married and another is divorced. Okay. But things comes a little bit different if we touch with the ordinal attributes. So what is the difference between nominal and ordinal attributes? In ordinal attributes, the value will have orders. So here, if you look at the small, medium, large, and extra large, it has some kind of order of scales. That means extra large is larger than large, large is larger than medium, and medium is larger than small. Okay, so this is kind of order, the order matters. Definitely, we can adopt the multi-way splits according to the number of distinct values contained in this parameter. Here, the parameter has 4 distinct values, small, medium, large, and extra large. Then we use a 4-way split. We can use 4-way split. We can also do the binary split. Okay. So here, we use some of examples. The binary split comes with some of the problem here. So the parameter has 4 distinct values. We definitely can separate these 4 values into a number of combination of 2 sets. We can do a 2x2 separation. That means we can group small and medium together, large and extra large together. We can do 1-3 separation. That means we're using small as one set and medium, large, and extra large as another. But we cannot do such kind of 2x2 separation. That means small stay with large, medium stay with extra large, because such kind of separation violates the order property. Okay. We want to describe the scale in order, so we cannot mix up the values in terms of the order. Okay. So here we can divide values into 2 subsets, but we need to preserve the order property among attributes values. That's the issue, that if you touch with the ordinal attributes, you want to adopt the binary split, the order will become some of the constraint to limit the number of combinations of the separation of those values into 2 sets. So if you have some of the continuous attributes, that could be the most complicated case. Continuous attributes means the attributes have continuous or real values. If you treat those values as distinct values, you could have like probably 1 million observations or even larger. So you want to do a kind of 1 million way splits, right? That could be so complicated and minimize the impact of the value. So if we want to appropriately split based on the continuous attributes, here some of the major strategies can be adopted for handling the split based on the continuous attributes. The first one is called discretization. So first we can apply the discretization strategy to form an ordinal category of attributes. That means we convert the continuous attributes to an ordinal categorical attributes. So ranges can be found by equal interval bucketing. That means you separate the whole range of the values into a number of equal intervals. Or you can also consider from the frequency perspective. You set the interval based on the equal frequency bucketing. Okay, that means the interval might not be equal, but the values contained in this interval will have the same frequency. Right? So this could help some of the data imbalance strategy. You will avoid some of the intervals that you almost have 0 observations, and some of the intervals you will have extremely large observations. Or last, you don't want to set up such kind of hash rules. You can apply clustering, okay, to divide the data into a number of clusters, so that you will have a categorical. You will have the categories. Each cluster is a category. Okay. And also, the application of such kind of discretization strategy could be two ways. Okay. One is the static discretization. That means you do one-time discretization at the beginning. Another is dynamic discretization. So this discretization will just happen by considering the value at a particular node. Then with the node develops and the tree develops, then this discretization will repeatedly or dynamically happen at each node. Okay. So the discretization basically aims to convert the continuous attributes to ordinal categorical attributes with a very finite number of categories. But if you want to cut it to a smaller number of categories, basically 2, then you can adopt the binary decision. That means setting up a threshold to break the whole interval into 2 parts. So this threshold will be just V value here. If the attributes less than V will be 1 category, and the attributes with values larger than or equal to V will be another category. Okay, so you consider all possible splits and finds the best card. The problem comes from like how to determine a appropriate V. Then you need to try different number of different options of V and find the best card. The best card means the best value of V to cut the values of the A into 2 parts. This is a kind of heuristic or search process, so it could be more computational intensive. So here we have an example, how to determine the best split. We have a data set here. The first column means the ID, the index of the data points from 1 to 20. And in the following, we have 3 inputs: gender, car type, and shirt size. And we want to do a classification task to determine the label of the class, whether it's C0 or C1. Okay. So before splitting, we can see that there will be 10 data points of class 0 and also 10 data points of class 1. The problem is that in this data set, we have 3 attributes. Okay, to grow a tree, every time we need to select one of the attributes and determine whether such kind of attributes can give us the best split. So how to determine the best splits, then later we will talk about 3 very famous measures. Okay. Here we can see, we can consider gender. Possibly we can consider each of them. Okay. we can consider gender. And if we find out gender, it just has binary values, male or female, okay? So if we determine, if we set up a test condition that the gender is equal to male, or yes, no means female, then we probably find out the C0 in the node, in the leaf, based on such kind of test condition. We have the number of C0 equal to 6 and number of C1 equal to 4 if we consider male. And based on this data set, we can count 1, 2, 3, 4, 5, 6, 6 C0, okay? And no, then we will find out C0. Actually, there are 4 C0 and 6 C1 in this based on such kind of rule. And if we consider car type, you will see that the car type have 3 values: family, sports, and luxury. So we can adopt a 3-way, okay? Then we can determine. We can also using the customer ID, which is 1 to 20. So if we use the customer ID, we will find out that in each node, we will have very clear decision, okay? For example, C1, then we will know that if a customer ID equal to C1, we will know that this customer must be C0, okay? The class will be C0. And if we using the class ID equal to 10, then this customer ID equal to 10, then the class will also be C0. So based on each of the class customer ID, we will have a clear observation of the decisions. So we can see that if we consider gender, the return of the results is very unclear because the ratio of the C0 and C1s contained in such kind of leaf is comparable, 6 versus 4. There's no dominating advantage. If we consider car type, we probably have some of kind of the advantage that we will find out the dominating class in each of the node. So if we say, if we know the car type of that customer, if the car type is family, we will say it has a high chance that the customer should belong to class 1, okay? But if we use customer ID as the criteria to do the splits, we do 20 split. Then we are very clear that it must be, okay? So if customer ID is 1, then we will know the customer must be with the class 0. Then which one probably will be the, which one can be considered as the best? Then next we will talk about how to determine how to evaluate the split. Why we say one type of split is the best. So basically, the splitting performance, we will use a term called impurity or purity to describe whether the split is good or not. So a high degree of impurity is illustrated here. That means if we have 2 classes, and based on a decision, we go to a decision node, which contains the equal number of 2 classes. This is super impure, okay? That means a high degree, probably the highest degree of impurity is so ambiguous. We cannot make a clear decision. And a low degree of impurity means the node is pure. That means the pure means that there's dominating evidence that the class should be intends to belong to 1 value, okay? Here, we can see that in this node, we have 2 classes, and one class has 9 records, another one has just one record, we will see that the C0 case dominating the C1 case. So if we follow that decision rules, go to this node, we will likely to make a decision that the data points should belong to class 0. Okay. So in growing a decision tree, we usually consider a greedy approach, which means the nodes with the purer class distribution are preferred. So we want to develop a tree that once we throw a data into this tree, you go to every nodes, those nodes should be pure. Okay, that means every node has one of the class as the dominating case. Then we know that each node, if we can find out case as the dominating case, then this node will be pure. But we don't want to just count by our eyes or using our hands. So we need to have some measure to every time measure the node impurity. And this measure can be a reference to the algorithms in growing a tree. Okay. Then next we would like to talk about 3 major measures of the node impurity, which include the Gini index, the entropy, and the misclassification error. So the Gini index is mathematically described as here. It's 1 minus summation of pi with t square with I equal to 0 to the c minus 1. So where PIT is the frequency of class I and node T. So T denotes the number of the nodes, and I denotes the number of the class, and this PIT is the frequency. So here the frequency can be converted as kind of probability. The number of times happens divided by the total number of times, okay? And the C is the total number of classes. So C minus 1 from 0 to C minus 1 means the total number of classes we summate them, okay? So the entropy is described a negative summation from class 0 to C minus 1. That means the total number of classes. And in each of the I, we will do a multiplication of the PIT multiply the log 2 PIT. Okay, so this is the entropy. And the misclassification error is equal to a very simple description, 1 minus max PIT. Okay, so the maximum value of the frequency of class I at node T, the largest probability. Okay. All right, so we will probably split here. Then next we will talk about how to make the split based on each of the measure of the node impurity. Okay, let's come back at 8 o'clock. All right, we take a break. Okay, let's come back and continue our lectures. All right, so we stopped at the introducing the measures of node impurity in the previous session. And then next, we will talk about how to using the impurity measures to do the split, to finding the best split. So in finding the best split, you can using either one of these three measures, okay? It does not matter which one, but you can pick one. So you need to compute. So in finding the best split, you need to compute the impurity measure twice. First, you need to compute the impurity measure before splitting. Okay, then you compute the impurity measure after splitting. So basically, it means like you compute impurity. So in compute impurity measures after splitting, you need to first compute impurity measure of each trial node. So when you do the splitting, you consider a parameter as a parent. Okay, then you divide, you split it and producing the nodes. Okay, so you can compute the impurity measure. So if you want to compute the impurity measure after splitting, then you need to compute the impurity measure at each of the trial nodes. Okay, then the M is the weighted impurity of trial node. So the impurity measure after splitting is a kind of weighted impurity of the trial node. So if you have impurity computed before splitting, which is at a parent, which is P, and after splitting, which is the M, then you will have the difference, okay? You can choose the attribute test condition that produce the high scan. You want to see that after splitting, whether you will get the highest knowledge gain through such kind of splitting, okay? That means if at the beginning, if the splitting is impure, then you want to expect that after splitting, things can become pure, okay? Or you add a splitting, okay? You will start at the point, and after that splitting, you can get very pure nodes, okay? So choose the attribute test condition that produce the highest gain, which is P minus M, or equivalently, the lowest impurity measure after splitting M. You want to making things pure, so you want to get the lowest impurity measure. So here is an example. So before splitting, we have class 0 and class 1, two classes, okay? And the frequency of class 0 is denoted as N00, and frequency at class 1 is denoted as N01, which is P, okay, which is P. So in this data set, okay, we have such kind of, based on each of the attributes, we will kind of such kind of P. So then if we have two attributes, we want to select the two splits. One is attribute A, another is attribute B. Then we need to determine whether we should choose A or we should choose B to do the split, okay? Before we get an answer, we have to try both. So first we try A, we do a split. Then we get two nodes, node N1 and node N2, okay? Then based on node N1, we got two classes in node N1. And the number of class 0, we use N10, denote the class 0 in this node N1. We use N11 to denote the number of class 1 in this node, in this N1, node N1. And for the node N2, we do the same thing. N2 will also contain two classes. Then we use n to 0 to denote the number of classes of 0 into in this node n2, and also n to 1 denote number of samples, okay, of class 1 in node n2. So based on node n1, we can compute an impurity measure which is called m11, and based on node n2, we will get an impurity measure m12. Then we take a weight, we weight them, okay. Then we got an impurity measure m1, and we will also do the same thing for the parameter b. We consider parameter b to build up the node to split. Then we also get the same impurity measure based on each of the nodes, and weight it. We using a weighted average, then we got M2. And how can we determine whether we should do that on attribute A or attribute B? We need to compute again, or sometimes we call information gain, which is the difference between the impurity measure before splitting P minus the impurity measure we obtained after splitting based on each of the attributes. Okay, so M1 is the impurity measure after splitting based on attribute A, and M2 is the impurity measure we obtained after splitting based on attribute B. All right, then we compare it again based on these two, and we find that one have the largest gain as the best split. Okay. Then this is a kind of general idea. Then we will go into details about how to do the computation based on different measures of impurity. We first talk about the Gini index. So a Gini index for a given node T is written as this. It's equal to 1 minus the summation of the frequency of class I at the node T and square, okay? So if we look at this value, its maximum will be 1 minus 1 over C, okay? The number of classes, 1 minus 1 over number of classes, when records are equally distributed among all classes, implying the least beneficial situation for classification. And the minimum of 0 when all records belong to one class, implying the most beneficial situation for classification. So you will see that this term, the worst case is 1 minus 1 over C. Okay, so that is a small value. And the best case is 1 minus 0. That means, which is very pure. Okay, so this is the impure case, a worst impure case, and the best pure case. So here we look into one example. Okay. So Gini index for given node T is expressed as this. We have seen in the previous lecture, we quoted here, so will be a good reference for you guys to check the example. So for two class problem, okay, we have one class frequency P, and that is 1 minus P. Okay, so the Gini index will be equal to 1 minus P square minus 1 minus P square, a square of the 1 minus P. So we rearrange it, then we will get it. The Gini index is equal to 2P multiplied 1 minus P. All right. Then we look at specific examples. If we have a node of two classes, in this node C1, the number of class 1 in this node is 0, and number of class 2 in this node is 6. Then what will be the Gini value in this node? It will be 0, right? It's listing here. And why it is 0? It is because P is equal to 0. Okay, it's 6 over 6, 0 over 0 plus 6, then it's 0. Okay, and 2 multiply 0 multiply 1 and it's equal to 0. So Gini is equal to 0 here. Then how about if the node has the number of class 1, which is equal to 1, and the number of class 2 in this node is 5, then what will be the Gini value? It will be equal to 0.278. Okay. Why is equal to 2.78? It's probably 2 multiply 1 over 6 and multiply 5 over 6. Okay. It's 5 over 18. Okay. Let me clear. So if we look at this example, 2 multiply 1 over 6 multiply 5 over 6. Okay. Who has a calculator? Help me to check whether it is equal to 0.278. Based on my memory, it should be like this. Okay. So 5 divided by 18. Anyone can confirm that it is equal to 0.278? It should be, right? Because if you consider 6 over 18, that's about 1 over 3. That's 0.33 something. And 5 over 18 should be 0.278. Yeah. Thank you, Haoling. Good job. So the P is the frequency. Basically, it's proportion. Okay. So it means the number of events over the number of total events. Okay. So for the third example, the P is equal to 2 over 6, which is equal to 1 over 3. Then its Gini is 2 multiply 1 over 3 multiply 2 over 3. Okay. And it's 4 over 9. All right. And the last one is 2 multiply 3 over 6 multiply 3 over 6. Okay. It's equal to 1 over 2, which is 0.5. All right. So the details are clear. Everyone got it, right? Very simple. Oh, the next slide shows the details of the calculation. So I can skip this slide because I've shown the details of the calculation. Then we have learned computing the impurity measure based on the Gini index based on each of the nodes. Then how can we compute the Gini index for a collection of nodes? That means based on one node P, then you do a K partitions. Then how can we compute the Gini based on such kind of split? Okay. Let me draw. We have a node P, then we do K partition. Here we set K equal to 2. That's a 2 partition. And how can we do the weighted average of the Gini based on the nodes? So we do a weighted average. Okay, for example, the N1 is equal to 4 and N2 is equal to 6. Then it should be 4/10 multiply the Gini 1 of the node 1, okay, plus 6/10 multiply the Gini of node 2. Okay, right? So this is a weighted average. So you see the previous slides, we say like integration of M by integrating M11, M12 into M1. So this is actually a step, weighted average, okay, based on the number of data points contained in each of the nodes. Then you will compute the weight. So here, the Ni means the number of records at child I, and N means the number of records at parent node P. That's the total number. So we choose the attributes which minimizes weighted average Gini index of the children. All right. So for the Gini index, the information gain will become larger if the weighted average Gini at the children's side is smaller. Okay. So Gini index is used in decision tree algorithms such as CART, classification and regression tree. All right. So here we have a full example about the binary attributes binary split, computing the Gini index. So we consider a parameter, attribute B, and we do a binary, we do a 2 partition because it is binary. So it will have 2 trial nodes, okay? So we want to seek the weighting partition to make the partition larger and pure, okay? So here we have the data show at the parent stage, the total number of data points are 12, and 7 of them becomes class 1, and 5 of them becomes class 2. So if we can compute the Gini at the parent side is equal to 0.486, okay, 0.486. Then we split it to 2 parts. Then we have to compute Gini at node 1 and at node 2. So after splitting, we can see that the total number of data points belongs to node 1 is 6, and total number of points belongs to node 2 is also 6. But in node 1, 5 of them belongs to class 1, and 1 of them becomes to class 2. But in node 2, 2 of them becomes to class 1, and 4 of them becomes to class 2. Okay, so we compute the Gini at M1, which is 1/5/6, 1 minus 5/6 square minus 1/6 square, which is 0.278. Okay, and for N2 is 0.44. Then the weighted Gini is 0.361. The weight is 6/12, right? Then we can compute again. So parents Gini is 0.486, and the children Gini is 0.361. Then we got again 0.125. All right. So this is the full version to compute again based on the Gini index. And in this example, we consider binary attributes, which is very simple. But what about if we consider categorical attributes, which might have multi-splits? Okay, then how can we compute the Gini index? Okay. So for each distinct value, gather counts for each class in the data set. Okay. And then we use the count matrix to make decisions. So here, this is the count matrix. Okay. Then we compare the multi-way split and two-way split. So if we have the multi-way split, okay, we split the node to 3 children, with each of the children in the children family. We have 4 data points belongs to this node, and 3 of them belongs to class 2 and 1 belongs to class 1. In sports, all 8 out of them becomes to class 1. And in luxury, 7 of them becomes class 2 and 1 belongs to class 1. So if we can compute the Gini for after splitting, it's 0.163. It matches this kind of results because it's pretty pure if we consider each of the node. But if we consider two-way split, once we integrate the supports and luxury as one set and family as another, this is very impure. If you see that in the nodes, sports and luxury, we have 9/7, which is almost equal, so it's impure. But if we consider another two-way splits, we leave sports as one and integrate family and luxury. Then we will see that one is pretty pure, another is 2 versus 10. It's getting much better, but still compare with a multi-way splits, which is 0.163, and this 0.167 is slightly higher. Okay. So here we will consider the multi-way split, which results in the minimal Gini value after splitting. Probably is the best or is a better option. But if we want to consider 2 options of two-way splits, and definitely the split strategies consider sports as one set and family luxury as another set is a better option. How about if we consider the continuous attributes? Okay, then how can we do the computing of the Gini index for the continuous attributes? Here we consider data sets, the 3 attributes: homeowner, marital status, and annual income. So the annual income is the continuous attributes. First, we need to consider the split strategy for the continuous attributes. Okay. So here we consider use binary decisions based on one value. That means we want to set up the V as the cutoff value. So there will be several choices for the splitting value. Okay. Which minus number of possible splitting values and equal the number of distinct values. Okay. And each splitting value has a count matrix associated with it. So class counts in each of the partitions. So based on the setting of the value of the V, then we will have the different count matrix for the split. So we can compare different count matrix to determine the best setting of the V. Okay. And there's a simple method to choose best V. So for each V, we scan the database to gather the count matrix and compute its Gini index. So the V results, the minimal Gini index will be considered. But it is computationally inefficient, and because it requires a lot of repetition of work. All right. So here we show the kind of search process, okay, find out the best splitting values. So for efficient computation for each attributes, we can adopt such kind of strategy to improve the efficiency of computation to determine the best value of V and for splitting these continuous attributes to two parts. First, we saw the attributes on value. So here you can see how many attributes here. 125, 170, 120, 95, 60, 220, 85, 75, and 90. So we can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 records. Okay, we saw that. Saw those attributes on values. And we set the split position. We linearly scan these values. And each time updating the CAM matrix and computing the Gini index, we set the split positions. So for example, equally 55, 65, 72, 80, 87, 92, 97, 110, 122, 172, and 230. Okay. So this 65, we just take an average between 67 and divide by 2, then 65. And 72, we take an average between 7 and 75, and this 72. Okay. And here, 60, we divide by 5 is 55, because here the you can see the 60 and 70 is increasing. We consider 65 as a position to split. So it's a 5 increase based on 60. Then its left side, we also use the 5 as the scale. Okay, so that means we have a V equal to 55. So we set the criteria of V to 55, then split it to a kind of value less than 55 and larger than 55. So for this 220, okay, so we set it to kind of 230. This is because kind of a larger increase, okay? So we can manually set it to a kind of a larger value by a 10 degree of increase, okay? Then based on each of the splitting value V, okay, then we can compute the counting, the count matrix. Then we compute the Gini index based on each of the count matrix, and we find out, okay, here, when we choose the V equal to 97, we obtain the lowest Gini value, okay, Gini index. So we set the V equal to 97 as the split criteria for splitting the continuous attributes to two parts. Okay. So that is the computation of the impurity measure based on the Gini index. Next, we will talk about the measure of impurity entropy. So if we consider entropy as the measure of the impurity for growing the tree, then how can we do the computation? Okay, so the computation of entropy is a little bit more complicated. First, let's look at how entropy is computed based on node T. So the entropy is actually an active value of the summation from class 0 to the number of classes. And for each of the class, we compute multiplication between the frequency P and the log 2 of that P. So PIT is the frequency of class I and node T, and C is the total number of classes. So for the entropy, the maximum of log 2C, the maximum is log 2C when the records are equally distributed among all classes, okay, implying the least beneficial situation for classification. That means the most impurity case will be resulting entropy equal to log 2C. And the best pure case will result in entropy equal to 0. So if entropy equal to 0 means it's very pure. and when all records belong to one class, implying most beneficial situation for classification. So entropy-based computations are very similar to the Gini index computations. Here, we look at one example. So that's also the 3 nodes we have seen before in the Gini index computation. But here we change the formula from Gini to the entropy. Again, we need to first compute the frequency or the proportion. So for this CAP matrix, we will find out the frequency P of class 1 is equal to 0 over 6, that's 0. And the P of class 2, which is 6 over 6, which is equal to 1. Then we will immediately compute the entropy, which is negative 0 multiplied log 0 minus 1 over log 1. So 0 multiplied log 0, which is equal to 0, and 1 multiplied log 1 equals 0, then which is also, so the total entropy is 0. Very pure, the purest case, entropy will equal to 0. Okay. If it is a little bit impure, in a case 1, 5, okay, we will see that entropy will be equal to 0.65, okay, by replacing the values of that equations. And for the very impure, a little bit more impure case, 2, 4 case, and the entropy equal to 0.92, okay. So from this case, you will see that the entropy is very sensitive to the increase of the impurity in each of the node. Okay, its value boosts very quickly if your node is a little bit impure. Okay. So once you compute the entropy at the children's site, you still need to follow the Gini idea. You need to weighted average. Okay, compute the entropy after splitting. Then you also need to compute the entropy before splitting. Then you compute the information gain, which is the gain split is equal to the entropy obtained before splitting and the entropy obtained after splitting. So at the parent node, P is split into K partition children, and Ni is the number of records in each node I. Okay. So by using the entropy, we want to choose the split that achieves the most reduction. That means have the highest gain. So this entropy or information gain strategy is widely utilized in the ID3 and C4.5 decision tree algorithms. And the information gain is the mutual information between the class variable and the splitting variable. Then here we can see, we can further go back to the problem with large number of partitions. In the previous example, we have shown that we can do split based on gender, which just have 2 values, binary values. We can also based on car type, do a 3-way split. And in a very extreme case, we consider customer ID as a criteria. We can do 20-way split. Okay. But it looks like 20-way split has the most pure case, okay, the purest case. And using car type, we can get a good pure, lowest, it's not the lowest, it's a much lower impurity, but not the lowest one, okay. So node impurity measures tend to prefer splits that result in large number of partitions, each being small but pure. So the customer ID has the highest information gain because entropy for all the children is 0. So if you're using entropy as a measure of impurity to grow the tree, then the class ID, the customer ID could be a nice choice because all the entropy at each of the nodes is equal to 0. So 1 minus 0. Okay. Then how can we handle this case? because this is really meaningless if you using customer ID as a criteria for making decisions. This is actually you treat every individual as a distinct agent, okay? And definitely everyone is unique. It cannot be duplicated. Then you don't have any conclusive knowledge from such kind of data, right? Then people design another metric, which is called gain ratio, to achieve a balance between the total weight of splits and the information gain. Okay. So it is the ratio between the information gain splits divided by the split information. So the split information is equal to a negative value of the summation of the number of data points in each of the, it's a proportion between the number of data points in the node and the total number of data points. Okay. So the parent node P is split into K partitions, and Ni is number of records in child node I. So this adjusts information gain by the entropy of the partition. So higher entropy partitions, that means a large number of small partitions can be penalized by this denominator, okay, by this split information. So we don't want it to see a very large number of partitions, but each partition has very low number of data points, okay? So this is used in C 4.5 algorithm. That's why C 4.5 is more powerful than ID3, okay? So this is designed to overcome the disadvantage of the information gain, which cannot distinguish, which will be played with such kind of very large number of splits, which results in every node is pure, but every node contains just one data point. Okay, that's give no conclusion. So we use the previous matrix count as an example, and then we compute the gain ratio. Okay, this is the gain ratio presented in the previous slides. Okay. I guess here I missed a negative sign. So the parent node P is split into a K partition. Here we use a car type as the parent node to split. We split it into 3. But we can also consider using car type to a binary split, okay, based on different separation strategy. All right. So here we have the split info for car type. 3-way splits is 152 and 0.163 over 1.52. And in previous example, we also find out if we do a binary split on the car type, but separating the values as sports as one set, family luxury as another, we will get a also very low Gini value, okay, which is 0.167, very close to 0.163, but it just have a 2 splits. But if we compute the split info is equal to 0.97. Okay, then if we compute the gain ratio, we will find out this strategy will be peaked, okay, because 0.167 over 0.97 will return a larger value than this one, okay, and this ratio. Okay, so that's the usage of gain ratio. We want to penalize such kind of situation. Okay, we want to penalize such kind of situation. And the last measure of impurity, which is classification error. Okay, that just describe how many classes are misclassified in this node. So the classification error at the node T is equal to 1 minus the max of the frequency. All right. So it's worth scenario that the most impurity case its maximum is also equal to 1 minus 1 over C if the records are equally distributed among all classes. Okay. And also, such kind of error will equal to 0 when all records belong to one class, implying the most interesting situation. So here is an example of computing error of a single node. We use a classification error as the measure of impurity. So in this example, we compute 2 P's because we just have 2 classes. And the frequency of class 1 is equal to 0 over 6 is 0. And for class 2 is equal to 1. Then we take the max frequency. Here is between 0 and 1. The max between 0 and 1 is 1. So 1 minus 1 is equal to 0. Okay, so that means this error becomes to 0 means the node is very pure. How about if we have the impurity case? So here we have 1, 5 case, and the frequency for class 1 is equal to 1 over 6, and for class 2 is 5 over 6. And the max between these two is 5 over 6, so its error is 1 over 6. And for 2, 4, the same principle is equal to 1 over 3, right? Then what is the difference between the 3 impurity measure? So you can see that if we consider misclassification error, okay, then the impurity of the with the increase of the frequency is kind of linear increase. Okay, so that means it is not distinguishable enough. But if we consider Gini, it has a quadratic a curvature term. Okay, that means this measurement can have a better distinguish if the impurity increase. Okay, the impurity increase faster. Okay, but entropy has the most sensitivity. Okay, increase sharply with the frequency increase. Okay, so misclassification error versus Gini index. We say that entropy has a most sensitive case. Gini and misclassification have the same worst value and best case. Okay, 0 to 0.5. Then if we consider this example, the parent has 2 classes, C1, C2, and its distribution is 7 versus 3. And the Gini before splitting is equal to 0.42. And after splits, we have 2 nodes, node 1 and node 2. And we have data points 3, data points 4 into node 1, and 7 records 4 into node 2. And this, we can compute the Gini at each of the nodes, and the Gini after splitting is 0.342. Okay. So the Gini actually improves, but the error remains the same. Okay. With the previous, did I show the error? Okay, I actually probably miss the slides which talks about the misclassification error based on this kind of case. Okay. So which basically we want to show that the misclassification error in this case cannot well distinguish. Okay, but the Gini index can. Okay. So if we have a kind of splitting case, okay, for these 2 cases, all right. So the misclassification error for all 3 cases are actually 0.3, but the Gini index can have distinctions between these the three cases. And next we talk about the decision tree based classification, the advantages and disadvantages. Okay. So advantages of tree based classification is it is inexpensive to construct. That means it is fast. Okay. Its computational load is low. Okay. And its implementation is very fast. It's extremely fast at classifying unknown records. And also you have a tree structure. So based on the tree structure, you actually has the logic to interpret, okay, how you are going to do the classification. But if you have an extremely large tree, then it becomes quite complicated. But for a small size tree, it is very easy to interpret. And the decision tree based algorithm is robust to noise, especially when methods to avoid overfitting are employed. So tree are easy to overfit, but you can also have some strategies like pruning trees to avoid overfitting. And well-trained tree is robust to noise and also can easily handle redundant or irrelevant attributes. So unless the attributes are interacting. So the disadvantages of the tree-based classification is the space of possible decision trees is exponentially large. Okay, you have too many combinations of possible splitting, and the greedy approaches are often unable to find the best tree. All right, so if you increase number of the dimensions, the tree will be overwhelmed and does not take into account interaction between attributes. Nowadays, so far, if we look at our previous example, every split, we consider just one attribute. We assume that the attributes, they're independent and do not have interaction. And what does interaction mean? That means we consider, for example, the multiplication of two attributes, okay, or integration of two attributes. If we consider such kind of combination, there will be even larger number of dimensions we need to handle in growing up the tree. Okay. And each decision boundary involves only a single attribute. Okay. So we have finished the decision tree based classification. Okay. Then let's take a break and we come back in 15 minutes, 9:03. Okay. Did I share my screen? No. Okay, class. So let's continue. So we have finished the one major content, which is decision tree. We introduced different measures of impurity for growing a tree. That means how can we choose parameters to split and generating children's for growing the tree. Okay, and later we are going to talk some other classifiers. First, we talk a very classical, commonly utilized classifier called k-nearest neighbor classifier or nearest neighbor classifier. So the nearest neighbor classifier comes from a basic idea that we will classify one thing to attack if all your friends or neighbors nearby you belong to that tag, okay, or the majority of your neighbors or similar items, they share the same tag, okay? So here the example is, if we want to test what is this record, if it walks like a duck, quacks like a duck, then it is probably a duck, okay? So we want to classify this test record and we check a number of its neighbors. This could includes like two chicks and 3 ducks, okay? Then we using a voting scheme and to consider that this record is a duck. So basically its logic is based on a test record, based on the distance to find out its k nearest neighbor first. Then based on the tag of the neighbors, we're using a voting scheme. The majority wins and the tag of the majority will be assigned to this test record. It's very simple, okay? So we use these slides as an example to better illustrate. So those negative and positive signs represents 2 classes of the data points that we have observed. Then this dot is the test data, which we don't know its tag, okay? Then how can we classify this unknown point based on based on the patterns of the data we observed? So to use the nearest neighbor classifier, it requires 3 things. First, we need to have a set of label records. That means the references, okay? Then second, we need to determine the distance metric we would like to use to compute distance between the records. And this distance majorly utilized to find out neighbors of this unknown data point. Then the third thing is we need to set the value of k, okay, to decide the number of nearest neighbors that we would like to find, we would like to use to make a decision of the class of these unknown data points. So basically the training, the only training step involved in nearest neighbor probably could be involved in 2 issues. The first is the selection of the distance matrix. If you have a number of distance matrix, based on the training, you will select the best one. Also determine the appropriate value of k, okay? You can specify k equal to 3, equal to 5. It should be odd number, okay? It could not be even number, otherwise you cannot make a decision, right? For example, you set k equal to 4, then 2 votes for positive and another 2 votes for negative. That's waste of time, right? So you consider 3, 5, 7, 9, 11, such kind of odd number. You will always give a winner, okay? Then based on this, after you getting all of these things, then you are able to classify any kinds of unknown records based on the following procedure. First, you compute distance of the unknown records to other training records, okay, to all the other training records. For example, here, compute the distance from these points to all the others, to everyone actually. All right. So I don't draw all, but just give you guys example. Okay. How many observations here? You compute how many distance. Then you do a sorting, do a comparison to identify k nearest neighbors. For example, k equal to 3, then that's it. If k equal to 5, then probably that's it. K equal to 9, then we probably equal to including some negative signs. Okay. And use class labels of the nearest neighbors to determine the class label of the unknown record. Basically, the majority vote. So you see that if we set k equal to 3, then 3 of its neighbors are all positive. Then we say this data points is assigned with the tag positive. Okay. So distance sometimes is also called proximity. So we have described that in previous clustering concept. So compute the distance between 2 points. Usually we can use Euclidean distance, but later we will show a case that Euclidean distance sometimes might not be sufficient. Okay. So usually we use Euclidean distance in the k nearest neighbor classification. Okay. And we determine the class from nearest neighbor list, take the majority vote of class labels among the k nearest neighbors. We can also assign weight. So another training issue is if we determine the number of k, and in some of the applications, we can consider assigning weight factor to different neighbors. Okay. So this weight factor can be directly set equal to 1 over the distance. That means the further, the lower. Okay. So if the distance is large, then the weight will be small. If the distance is small, that means close, then the weight will be large. But you can also use in training to determine a dynamic setting of the weight, not just 1 over d squared. Okay, you can dynamically determine the weights of the different neighbors according to training. So in k-nearest neighbor classification, selecting appropriate value of k is also very important. Using this as an extreme example, if we set k equal to 5, then it could be just like this. Then we will determine that this unknown data point is positive. Okay. But if the k is too large, then we can find out the assignment of the tag will be completely reversed. Okay, from positive to negative, because once you have a very large number of neighbors, then negative becomes more. Okay. And also choose of the distance is very important. Here, if we have 2 examples, 2 data points. One data point has all value equal to 1, but last one equal to 0. They differ just in 2 digits with 1 to 0. But another data points, all of them are set equal to 0, and last digit is 1, and another is first equal to 1, and all the others 0. These are actually 2 examples, but if we use Euclidean distance, it will all be 1.4142 for both pairs. They will have no difference. So in these cases, typically, if you consider data of like a binary streams or kind of a set of categorical data, those value does not matter, but the value category matters, then you might consider choosing cosine, okay, as a distance measure, which will be better than correlation or Euclidean distance. Or sometimes using the Manhattan distance, okay? So to talk a little bit more about the nearest neighbor classifier. So basically, the nearest neighbor classifier is a classifier which does not require training. All right. Why it does not require training? Because if you have determined the distance metric and you determine the value of k, you already can directly apply this algorithm into a new data set. Okay. You don't need to have a training phase. So for every unknown data point, every test data points, you just compute this its distance to every one of the observed data points. And according to k, find out its neighborhood and make voting. Okay, for every testing record. So k-nearest neighbor is extremely easy to apply, but it has a very big disadvantage. What is its disadvantage? Its disadvantage comes from its computation. So given any of the new data points that we want to classify, it needs to compute its distance to every one of the observed data points. Okay. And then you need to, according k, to do a sorting, to do a ranking and find out the k nearest neighbors, then make voting. Then why it is troubleful? Assume you have an observed data set which has 1 million records. Then you have a new data coming in. You need to compute its distance to each of these million records. That means you need to compute 1 million distances. All right. Then you need to find out the k nearest neighbor one in this million records. That means you need to do a sorting of the million records and find out the top 3 or top 5. Each of such kind of implementation could be very time consuming. So in implementing the k nearest neighbors, it's better that you have a smaller size, but have a high diversity of samples in this observed data set. Okay, don't use a very large data set. It could be very computationally extensive. Okay. Another is you need to do it for every data point. Okay, another side is you need to do it for every unknown data point. If you want to test a big unknown data set, which has 1 million records, this testing process, every data point have a computational requirements. Then completing the computation of these 1 million records could also be very time consuming. Okay. So the majority of the complexity, computational complexity in k-nearest neighbors is directly related to the number of data points involved. Okay. Next, let's talk about, so we finished k-nearest neighbors. Okay, then we will go into the Bayes classifier, which is a probabilistic framework for solving classification problems. So to understand Bayes classifier, first we need to know what is conditional probability. Then next, what is the Bayes theorem? So assume we have 2 types of conditional cases: event y conditioned on event x, or event x conditional on event y. And the conditional probability of event y conditional event x is py conditional on x. And it is equal to the joint probability of x and y divided by the condition, which is the probability of x. And for the conditional probability x depend on y, also the same thing, similar thing, okay? So the Bayes theorem is that given 2 conditional probabilities, py conditional on x and px conditional on y, as well as the probability of event x and the probability of event y, then we will have the conditional probability that y conditional on x is equal to the conditional probability x conditional on y multiply the probability of y divided by probability of x. Okay, this is the Bayes theorem. I guess everyone of you if you take any of the statistical courses at the bachelor, undergraduate level, you will know it. Then how can we using such kind of Bayes theorem for classification? We need to reformulate the classification task from the probabilistic way. So basically, we consider each attribute and class label as random variables first. Then given a record with attributes x1 to xd, that d means the total number of dimension. Okay, here is x3, x1, x2, x3. And the goal is to predict the class y. Basically, the prediction of class y means we want to find out a value of y which returns the maximal of the probability that y condition on x1, x2 to xd. So for example, in classification, y can have, here we have binary values, y equal to no or y equal to yes. Then we compare y equal to yes condition on this x and compare with the probability that y equal to no condition on this x. Then we pick one with a larger value as the class. Okay. All right. So the logic is clear now in a probabilistic formulation of the classification task. The next question comes from, we want to select a y which has the maximal py condition on x1, x2 to xd. Then how can we estimate such kind of conditional probability, y condition on x1 to xd from data? Here we use an example, given a record x with refund equal to no, marital status equal to divorced, income equal to 120K. Then can we estimate P, the y here is evade equal to yes, condition on such kind of x, and the probability that evades equal to no, condition on such kind of x. Okay. So here, to avoid the complexity, we replace evade equal to yes by yes and evade to equal to no by no. Okay. So basically, we will, in the letter, we will talk about probability yes condition on x and probability no condition on x, which means the evade equal to yes or evade equal to no. Okay. Then we use Bayes theorem for classification. We first compute the posterior probability, that probability y condition on x1, x2 to xd using the Bayes theorem, which is equal to the likelihood, which is probability that the join of the events x1 to xd condition on y, then multiply the probability of y and divide by such kind of join probability. Okay. Then we want to find out a maximum posterior. We choose y that maximizes such kind of posterior probability. So such kind of choosing y maximizing such kind of posterior probability is equivalent to choosing value of y that maximize this likelihood multiplied the probability of y. Okay. Why? Because the bottom one is similar, is the same for every type of y. Okay, the bottom one is similar to every type of y. So only the bottom, only the top matters. So only this product term matters. The bottom one is same. Okay, same for every y. Every y. Okay, and this one matters. So basically the top term determines, so this one determines, okay. All right. So we can say it is equivalent to choosing value of y, which maximize this term. Then problems comes from maximizing this term to maximizing this term, to maximizing this product of likelihood and probability of y. Then probability of y is easy to be counted from the database. Then the problem is, how can we estimate this term? Okay, this likelihood. Here we're using an example to illustrate the previous thing I've talked about. So you can see the bottom, they are the same. So the only top matters. So only the top matters, okay? Then the problem again is how can we compute this PX condition on y equal to yes or condition on y equal to no? Then we need to adopt the naive Bayes theorem to generate the naive Bayes classifier. So the naive Bayes assumption will be adopted here, which means among all attributes xi, they will be independent. So once they are independent, this likelihood will be written as a multiplication of each of the term. Okay, this joint probability will be the multiplication of the a set of conditional probability. Okay, right? Then how can we estimate the probability xi condition on yj? Okay, for all xi and yj combinations from the training data. And the new point is classified to yj if this py multiply the multiplication of all of those conditional probability is maximal. Okay. And here we're using this example. Given test record, x equal to refund, equal to no, marital status equal to divorced, income equal to 120K, then the likelihood will be decomposed to 3 terms. The conditional probability that refund equal to no, condition on y equal to yes, evade equal to yes, and right, divorce originally is P refund equal to no, marital status equal to divorced, and income equal to 120K, condition on yes, right? Then it becomes this, a multiplication of 3 terms, okay? And for evade equal to no, the same thing. Okay, you do such kind of decomposition by adopting the naive Bayes assumption. All right. First, let's look at how to compute PY. So PY is just counting the observations in this database. It's just fraction of instances of class equal to Y. Of class of Y, okay? So this Y have 2 values, yes or no. So you can see there are 3 observations of yes and 7 observations of no. So the PY for Y equal to no is 0.7, for Y equal to yes is equal to 0.3. They have about categorical attributes, PXI equal to C condition on Y. Yeah, it's basically the number of such kind of xi equal to c divided by the total number n. Okay, so for y equal to here you need to differentiate. Okay, this n equals to the total number of y equal to one of the value, y yes or y equal to no. Okay. So in these data sets, y no is equal to 7. So if y equal to no, then it is 7. Okay. If it is y equal to yes, then n equal to 3. Okay. So where xi equal to c, absolute value is the number of instances having attributes value xi equal to c and belonging to class Y. So example, P status equal to marital status equal to married, condition no. You need to look at Y equal to no, 7 records. Then you further check the marital status married, which is 4. Okay, 4/7. The same thing, refine equal to yes and Y equal to yes is 0/3. Okay, so it's 0. Right. You check the number of combinations. And estimate probability from data. If we have the continuous attributes, then how can we deal with it? In the previous example, we deal with the categorical attributes. Then how about continuous attributes? The same thing. It's like the splitting in the tree. We can do first discretization of the continuous attributes. So we'll partition the range into bins and place continuous value with bin value. Okay, attribute change from continuous to ordinal. Or we can do probability density estimation. We assume the attribute follows a normal distribution and use data to estimate parameters of the distribution. For example, using data to estimate mean or standard deviation. So once the probability distribution is known, then we can use that distribution to estimate the conditional probability P xi conditional Y. So estimate probability from data, we consider the continuous attributes. We adopt the probability density estimation. Here, we assume that probability xi conditional yj follows normal distribution. Then 2 parameters need to attributes includes the sigma and the mu. Okay. So for the data that income and class equal to no, the evade class to no, and the income we consider taxable income, we will find that its mean is like 110. Okay, we consider all the no, and the sample variance is equal to 2,975. So how many do we have? Data points that we have for the class equal to no? We have such kind of 7 records. Then we can compute the sample mean and sample variance. Okay. Then we can have this normal distribution to estimate the probability of income equal to 120, but condition on Y equal to no. Okay, which we replace X with this 120, and we obtain the mu and sigma here. Okay, then we can compute that its probability is 0.0072. This is an example. We adopt the naive Bayes classifier, the full process of computation for classifying this test record, X equal to X with value refined equal to no, marital status equal to divorced, and income equal to 120. Okay. So what should we compute? We compute each of the conditional probability. Okay, so for Y, the evade equal to no and evade equal to yes, there are 3 terms. Okay, so we compute these 3 terms for marital. And for the refund, we have 2 cases. Okay, so we can compute the computation. And for the income case, we use a distribution to compute the probability. Okay, for those categorical case, we do counting the frequency. Okay, so for the income, for each class, we get the mean and the variance. Okay, then we multiply all results together. So we can see the P refund equal to no, conditional no, with this 4/7. P divorce, conditional no. Marital status equal to divorce, conditional no, 1/7. Income equal to 120K, conditional no, 0.0072. then we can compute this PX conditional no. And same procedure applied, PX conditional yes. All right. Then we compute the multiplication of PX conditional no multiplied P no. That means E weight equal to no. Okay. And what is P no? MPS 7/10 and 3/10, right? So here we will know that this term has a larger value, so the class is equal to no. Okay. All right, so finish the base classifier here. I guess I can call it a day. The later story will take a longer time. So we probably start here. Okay. Any questions and comments? If no, then I will see you guys next week. Yeah. Very nice. See you guys online next week. Have a good night. Could we have some exercise for self-practice? I don't have exercise for you. You can check the slides. The slides have quite a number of examples. You play with it. Okay. This is a happy course, so we don't have exercise. All right. That's it. See you guys. Bye-bye. Yes, please. The data, but yes, for example, in the test, I will give you a sample data set. And definitely you need to do a counting of the events and compute the Gini index by yourself. It's not difficult, right? The Gini index, you count in the frequency and you compute it. The difficult part comes from the entropy side. You need to do a log. Then that you might need a calculator. Yeah. And otherwise you don't need. And also for the naive Bayes classifier example, you see like we have a full version of calculation procedure here. You just follow the example and you will know what to do first and next, and finally you get results. Yeah.